Good morning. So today I'm going to talk about most of our recent achievements in our division. Okay, fine. So this, thank you. As the outline of the talk, I briefly introduce some goals of our division in our team, our recent results and publications on these subjects here, and also some accomplished and future activities. So the strategies to convert solar energy, here is the most important three strategies. As you can see here, you have the photosynthesis. In the middle, have for instance a photoelectrochemical cell, and here on the right you see a photovoltaic device. So our division is going to be concentrating in studying not only the photovoltaic device, but most of the projects are actually related to using the photoelectrochemical cells in order to, for instance, to break the water molecule or even to reduce CO2. I think Rubens has already presented this slide. So the goals of our division is actually to understand the fundamentals of the main solar-driven routes to sensitize these dense energy carriers, and using in situ techniques. What I mean by in situ techniques is like electrochemical and also photoelectrochemical in situ techniques, and also imaging, transmission microscopy, and also synchrotron characterizations. And also we're planning to sensitize new novel materials, new catalysts, and new interfaces in order to boost the production of these dense energy carriers. And also we have a project on perovskite solar cells that wants to, starting for the small devices, also we are planning to go to large scale devices in order to boost the efficiency of all of these processes. So this is my team. So we have, besides my project, I have another 4 projects. These are the other co-PIs. Professor Ernesto Pereira from Federal University of São Carlos. His project is about synthesis of new functional materials for water splitting. And then project number 3 is Dr. Pablo Fernandez from here, from the Chemistry Institute at the Unicamp. Pablo and Professor also Nagal, that is also here, they're responsible for these inoperando techniques in order to understand more about the fundamentals of these electrochemical and photoelectrochemical reactions. And then also in project number 4 is Dr. Claudia Longo, also from the Chemistry Institute here at Unicamp. So Professor Claudia Longo is in charge of sensitize new materials in order to analyze materials for CO2 photo reduction. And then finally, we have a project number 4, is also development of new materials for water splitting from Dr. Flávio Leandro de Souza from the Federal University of ABC. So I'll show now some recent results also in the area of perovskite solar cells and perovskite materials. So of course, I'm not going to in detail because I don't have time, but just briefly to introduce the perovskite solar cells, why they are so important. If you look at this graph here from NRL, you see that now perovskite solar cells is this yellow dot here, has surpassed the polycrystalline silicon in terms of efficiency. So now the efficiency is about 23.7%. So it was a huge increase in the last years, and why we had such a improvement in efficiency in just like only like, let's say like in the last 5-6 years, especially because the scientists were able actually in order to achieve this efficiency, the scientists actually work a lot on the perovskite compositions and also to understand the interfaces in these devices, and also in the film is really important. The film engineering was really important in order to boost the efficiencies to this higher than 23% now. So the most efficient devices are actually based on these multiple cations in the structure. When you have like organic cations, you have inorganic cations. And one question that actually drove our attention since the beginning when we're planning this project was like, as we have so many, we have hybrid materials, we have organic and inorganic cations. So actually, what's the composition at a nanoscale? So this was the work from from my PhD student, Rodrigo. Rodrigo now he's leaving to the end of this week to a PFL. He's going to stay there for like 1 year in order to make like a 20% efficiency solar cells. So Rodrigo used this nano-infrared technique in collaboration with his synchrotron here in Brazil in order to investigate the nanoscale composition of these films. So in this case, we use the synchrotron light, infrared light, together with his known technique. This is what we call like nano-infrared. So basically what we have this film, this is a perovskite film containing organic, inorganic cations, and we shine like synchrotron light on this film. You probe like with AFM tip. So basically, the response here is actually the scattering is the infrared light, the scattering of the infrared light. Just to give an example, what we can get from this technique, this is the normal AFM topography, but also this is what we call like the infrared broadband image. You can see here you have resolution because they're using the snow, so we have a resolution of 25 nanometers. As you can see here, you see that some grains of the perovskite has more activity than the other grains. So it's important that as you are probing the scattering of the infrared light means that when you have these brighter colors, mean like more infrared light is actually reaching the detector. And if you remember, like the infrared light, it means that we have less organic material, less organic, let's say, components here when you see in the grain when it's this much more brighter than in the dark regions. So if you think about perovskite, it's not easy to prepare them, especially because, of course, the desired structure that you want is the cubic perovskite, but along with the preparation is very easy in the lab to have like not only the cubic perovskite, but what we call like these hexagonal phases. Sometimes also we have some remaining of lead iodide. So it's really complicated in order to understand this morphology and especially how all of these structures are actually distributed in this film. So what is nice from this technique is actually, these results we just submit to the Science Advances. We are just very happy because we just got a very positive response from the reviewers, and we hope that's going to be published soon. So what is interesting from this technique is actually you can go grain by grain and take just one single nano-infrared spectrum. As you can see, in our case, in our work, we are probing this organic cation, the stretching of the carbon-nitrogen bond. As you can see here, this is the standard infrared, the far-field infrared. This is what we call like our nano-infrared spectrum. So this peak here corresponds to this stretch of the carbon-nitrogen bond. So as you can see here, then you can go to our film. This is a film, as I told you, is composed by cesium, methylammonium, formamidinium. So those are organic cations. So we can go like grain by grain and take like what we call like a single infrared spectrum. So in some of the grains, you can see here, we see the signal from the organic cation. Other grains we didn't see. So this means that these grains are different in composition. And of course, it's also we use like other techniques in order to confirm that we believe that those grains are actually lead iodide in the film, this in the fresh film. And when we remove the cesium, that's interesting because using the high resolution X-ray, we see that in these films here we have a lot of the yellow phases. As you can see here now, when we're probing this, the morphology is quite different because you see that the shape of the grains are different. It means that there is not lead iodide anymore. These grains are more hexagonal. But actually, even in the background, in this bluish background, and even these greener grains, you see the peak of corresponding to Fa. So we have the organic, but if you look at here, the absorptivity of these grains are different. So we believe that these grains is actually are perovskite yellow phases. And for the first time, we were able actually in the literature to recognize, okay, this is a grain that is composed majority by yellow phase, and the other grain is more like lead iodide. And also we're doing some development on perovskite's efficiency, of course. This work is being doing by the new postdoc that joined our group, Kaká, and also Rodrigo is here, and also have another PhD student, Paul is also working in order to improve the efficiency of this device. This was our publication in 2017, and then the record was about 12.9% of efficiency for the perovskite. You can see here, although we reach about 13%, is a wide distribution of the efficiencies, and I'm very happy to say that in less than 2 months of work in our lab, we managed to increase the efficiency to almost 16% now. And what more interesting is actually we narrowed this distribution of the efficiency. So I promised to FAPESP and Shell that to July we're going to reach 18, 19%. I think we are on the way because the new glove box just arrived. They were already installed. So I think we are on the way to make like a very high efficiency perovskite solar cells. And also I'm going to present the work from Dr. Cláudia Longo here from the Chemistry Institute. So Cláudia is developing these materials for CO2 photoreduction. So here is Cláudia. So this work is being doing by her postdoc, Miguel Galante. So in these new materials are some oxides based on bismuth, silver, and tungsten. If you look at here, we call these materials quaternary complex oxides. What is very interesting, because if you look, when you look here to this energy diagram, adding not only bismuth to this tungsten oxide, but also silver, you can actually shift not only the valence band, but also the conduction band. And then you can see here now we have this driving force in order to, for instance, to not reduce only CO2, but also to produce, for instance, hydrogen. And in the previous work from the group of Professor Cláudia Longo, they have published this very nice paper. And when they show that this kind of materials here, these very complex oxides, they have a p-type behavior. So if it's a p-type, means that you can use this as a photocathode in order to drive, for instance, CO2 photoreduction. So what Miguel is doing now in the lab, he's actually working on this new mixed valence copper tungsten oxide. So it's important to say here that the copper here, they managed to sensitize not only copper 2, but also copper 1. And this is material with a broad light absorption in the whole visible range of the spectrum. And they are just in the final revision. They are submitting this paper, I think, this next month to Chemical Communication. And what is interesting from these materials, like according to the XPS, we can actually form copper 1, copper 2. Copper 1 is really important for the CO2 photoreduction. This was confirmed by XPS. But also, you see here in the photoelectrochemistry, you see a p-type behavior, because you see this photocurrent evolution here when you apply a negative bias in this material. And also using light and apply a bias here, you see here the reduction of CO2, you see the production of CO here. And also some work on, I thought I would present some work that we're doing in collaboration here with Professor Leandro from the Flávio Leandro from Federal University of ABC. Okay, first, okay, just a moment. Okay, first, I'm going to present the work from project number 1 from Professor Lúcia Mascaro. So Professor Lucas Mascaro in Federal University in São Carlos, she's developing metal-doped chalcogenides for water splitting reactions. So in São Carlos, they have been using this technique, what we call like a double post electrodeposition. In this case, Professor Lúcia and her postdoc Marcos, they developed this film, is copper gallium selenide, that was deposited on a FTO. What's interesting from this technique is actually you can guarantee the quality of these materials. And for instance, using this technique, you don't see like impurities like copper sulfide. These are the morphologies for these materials using this technique. So it's just a one-step electrochemical deposition with no additional steps in order to introduce sulfur. The composition was actually improved using this technique, not only purity, but also in terms of stoichiometry. This is really important. So this paper was just published on, in Can it's a separate publication now in the Can Electron. I'm not sure if it's online yet. As you can see, this material has this very nice band gap. So the next steps from the group of Professor Lúcia Mascaro is actually to use this, doping this material with bismuth, antimony, and niobium in order to make like solar cells. But also they're planning to introduce materials as a photocathode, because it's a P-type, and in order to use these materials for a CO2 photoreduction. Okay, now moving to this very nice collaboration with Professor Flávio in the Federal University of ABC. For the last years, we observed that the materials are very interesting for water splitting. And this was a work that we did in the past. So Mauricio joined the division, the project number 5. But at that time, Mauricio was in my group doing a postdoc. And we did this very nice work using these 2D materials for a hydrogen evolution. This was a titanate. What we did was in order to improve, of course, to increase the area of these materials, we introduced some what we call like nanopillars of titanium in this film. And we were able, using like very cheap catalysts like nickel oxide, we're able to actually to achieve like about 1,000 like micromole of hydrogen production, suspending this photocatalyst in this using this medium here. So this was what we call attention that for the first time we were able actually to pilarize what these materials, and we are front cover of this sustainable energy fuels and last year. So following this, using these 2 materials, so recently we just published, I think this is already online, I think it was published this month in Journal of Catalysis. This work that it was done by Saulo. Saulo is a PhD student in my group, this is Flávio. So what we did here was to use the graphene in order to improve the photocatalytic properties of these hematite photoanodes. So the strategy here, of course, was to sensitize the hematite nanorods. And after sensitize, then we cover the surface with actually a very thin layer, just 1 or 2 layers of graphene. It was not reduced graphene oxide, it was pure graphene. So as you can see here, we see improvement not only in the photocurrent, but also we decrease the onset voltage for the water splitting reactions. And as you can see also the increase in the photocurrent, but also in the stability. When we use this material as a cover layer of this hematite photoanodes, you see also a great improvement in stability. But it was interesting from this work is like we employ many techniques because in all of in the literature we know that graphene and reduced graphene oxide they improve the photocatalytic properties of these photoanodes or photocathodes, but it's really difficult to understand why. So using these 3 different techniques, for instance, the surface photovoltage spectroscopy, the transient absorption spectroscopy, and electrochemical impedance, we are able to actually reveal the whole of the graphene in the hematite. These are very interesting. These 2 techniques, for instance, surface photovoltage, the surface photovoltage, this one here, we can actually probe electrons. You see improvement in the number of electrons after incorporating the graphene, and with the transient absorption spectroscopy, we probe the holes. So we have 2 different techniques, one to probe the holes, another one to probe the electrons. And in both cases, you see increase in the density of these charge carriers after using the graphene. So we proposed here what they're doing is like the graphene layer on the top is actually decreasing the charge recombination. And in this case here, when we enhance the whole collection, that's the reason that you have such increase in the photocurrent of this system. And finally, some results in operando techniques. So this is the project number 3 that's being carried out also in the chemistry by Dr. Pablo and Dr. Rafael Nagal. they have all of these techniques here, like we call it sometimes in situ, sometimes operando techniques. I divide this table because it's an electrochemical cell and a photoelectrochemical cell. As you can see here, the group has already developed all the electrochemical cell to make all of these techniques, from the ellipse microscopy for surface imaging, differential electrochemical mass spectrometry, as also the sample collector that it can couple to HPLC, NMR, infrared. This is also electrochemical cell for X-ray absorption and diffraction, use the synchrotron light, and also for HAMA and cars in situ. So all of the electrochemical cells were developed, they're ready. Some of the photoelectrochemical cells are still in progress here. I'll show one of these electrochemical cell that the group is planning to patent. So you can see here changing. This will insert the counter electrode, the reference electrode, your sample just here. Changing the window, for instance, you can actually, you are able to use the same electrochemical and or photoelectrochemical cell for these techniques. Just an example of a recent result from the result from the group of Professor Pablo. Here you can see simultaneously they were able to see the oxidation of glycerol on gold, and at the same time they can probe actually by infrared the results, the conversion products of the glycerol to carbonates and glycerate using seeing here for the growing and the bands related to these products. And also in this last 6 months, we had in the Chemistry Institute, we had 2 graduate and 2 undergraduate courses on new energies and photoelectrochemical cells. It was given by me and also by Professor Claudia Longo. Maybe you can recognize here someone, is Fabio. So it was Dr. Tebano from the CTI. Also, Tebano spoke about displays. And Fabio gave us a very nice scenario of this division on methane to products. So it was very interesting. I think in total we had more than around 30 students that attended these 4 courses. So the future activities and projects. So we're planning our first workshop, like in 2 weeks from now. So many experiments are already planned to be carried out in the synchrotron this semester, like in situ X-ray absorption spectroscopy, in situ GWOX, into deep perovskites, and also have experiments to be carried out in MAX4 in Sweden. We hope to have between 12 and 14 manuscripts to be submitted to July. New collaborations have just popped up, like for instance, collaboration with this company in Brazil that is doing this very large area, OPV. We are just in contact with them in order to see if we can establish a collaboration, because they have the largest production line of OPV, and they are very interested in also in joining us in the project with perovskites. Most of the labs innovation are expected to be finished soon. We still have some equipment that are arriving, but most of them, not most of it, let's say most of them I've already installed, and I think that's it. And thank you very much for your attention.